All right, so looking at part 3, is it? I lose count sometimes. Yes, this is part 3 of partial fractions, or maybe a more complete term, partial fraction decomposition, where we do integrals by taking some fraction of some kind and reducing it to smaller and simpler parts. All right. Okay, so this time we're looking at something that it may look similar to others that I've showed you in part 1 and 2, but this one's quite a bit different, all right? So there's something about these that we need to notice before we even get started. The degree of the bottom part must be more than the degree of the top in order to use partial fraction decomposition, okay? If it isn't, like in this case, the degree down there is not bigger than the degree up there. The highest exponent here is not more than the highest exponent there. They're equal. All right? If that's not the case, then we divide this expression out. Okay? All right, so we will have to divide this one before we proceed at all. But I thought that, given that we're going to have to do that, and I'll show you a few problems anyway that involve that, it might be best to do like a review of long division. It can't hurt, and if you don't need the review, then you can skip this part of the video. It's not like we're in class and you got to sit through it. If you don't need it, you go forth to where we pick up with that problem. So say that you have something like this, and we would like to divide it. You could think of this like it's improper fraction, and if you divide it, you get a mixed number. By analogy, we might say, well, this is kind of like if you were going to say take 22 and divide by 7. Okay, that's an improper fraction, and we could divide into a mixed number. The technique is long division, and so it looks something like this. We say 7 into 22, and so I want to multiply something by 7 not to exceed 22, and so I got 3, and that's 21, and we're subtracting, I get 1, all right? So my answer is that 22 over 7 is 3 and 1 over 7. In a mixed number, when we say and, we mean plus. 3 and 1/7 is 3 plus 1 over 7. It's the quotient plus the remainder over the divisor. Dividing polynomials works much the same way, okay? All right, so here goes. We will do like this. I'll take x minus 4, and I will divide into, in much the same fashion I did over there, x squared plus 5x plus 6. Okay, so the technique goes something like this. I want to choose something to put here, such that when I multiply it by this, I will match the leading term. Notice I wrote these terms in order of degree, 2, 1, and 0. So I want to choose something to multiply x minus 4 by so that it will match that leading term there, x squared. And that would be x, okay? X times x minus 4. Now that I've chosen that, is x squared minus 4x. Okay, so there we are. I make this choice. I multiply. And sure enough, these do match, all right? After that, well, it's a lot like this in many ways. I choose the 3. I multiply the 3 by the 7. I get 21, and then I take 22, subtract 21, okay? With the subtraction here, you have to keep track of this being algebra, the fact that some of the terms are already negative. So this is like, that will be subtraction, but given that this is already negative, that will be addition. So I'm writing the operative sign there in red ink, okay? So x squared minus x squared, that cancels, and that was the objective, is to get that to cancel. Given that they match, they cancel when you subtract. In this, I get 5x plus 4x, so I get 9x. And then I guess you could say I have 6 and 0, okay? So I just get 6, 9x plus 6. Now, I repeat this process, okay? I now look at this and say, what do you multiply x minus 4 by to match that 9x? And that's going to be a 9, right? And if I multiply, I get 9x minus 36. Okay. All right. So now I subtract. This will look this way and this way. Okay, so I'll get 42. That's the remainder right there. We will stop this process when this is one less in degree than that. Meaning if this has the first power, when this number is a constant, we'll stop. Okay. All right, so let's see. How did that one work? It was 3 and 1/7. 3 plus 1 over 7. This works the same way. Is going to be x plus 9 plus 42 over x minus 4. Okay? All right. So that's the mixed number. That's the improper fraction. That's the way division works. Now, you'll find that these also work the same way this way. If I take 7 times 3 and 1 over 7, I should get 22, do I? What's 7 times 3 is 21. What's 7 times 1 over 7? It's 1. 21 plus 1 is 22. Same thing here. If you take x minus 4 times x plus 9 and then add 42, you'll get that top part right there. Okay? All right. So anyway, let me give you this as my answer. There's a very quick reminder about how long division works. Okay? All right. Now let's go back to this one. Let's say that I've established that for this, because this power is not more than that one up there, we need to divide it out. So let's go ahead and do that. We'll take x squared minus 2x minus 1. And I'll divide like so. And you might notice like everything has a place value. X squared, x, constant, x squared, x. If it helps you feel better, you can put a 0 in the constant column. But everything is organized when we do this. All right, so the procedure here is the same, where I need to choose something to multiply by this to match that leading term. That would be a 1, right? 1 times x squared is x squared. So I make that choice. I multiply. All right. And then I subtract. So this gets subtracted, but this gets added, and so does that. All right. So I will get negative x, okay, plus 1. All right. And then this becomes a mixed number. All right, so let's take this and say that when you divide this out, you get 1 plus negative x plus 1 over x squared minus 2x minus 1. We're going to see a mixed number right there. Okay? So, all right, here it goes. So here's my problem at this point. This as a mixed number, 1 plus negative x plus 1 over x squared minus 2x minus 1. Okay? All right. So if it helps you, if you like to make notes and keep track of things, this is immediately from my division. Okay? And then, like, it might be that I do this part by partial fraction decomposition, or maybe some other method. I'll have to look at this and decide how I should do it. All right? Now, when I look at this, you know, obviously the 1's not a problem. But these look similar in a way that, what's the derivative of this? X squared minus 2x minus 1. Derivative would be 2x minus 2. And I think I can make this work with a u substitution. Let's do something though. Let's factor out a negative 1 there and write it as a subtraction. Okay? So that's a little bit different than what we got with our division, but I think it will work better with the u substitution. So I factored out a negative 1 from what I had, and that negative 1 here in front of that fraction will be a subtraction. Okay, that is u substitution. Let's look at it in more detail. It's u substitution because if that's u, du is 2x minus 2. What do you get if you multiply this by 2? You get 2x minus 2, so that means that we can make it work with u substitution. All right, so say I'm going to take, let's just look at this part right here. X minus 1 over x squared minus 2x minus 1. Okay, so yes, that is u substitution. Here's how. U is x squared minus 2x minus 1. Du is 2x minus 2 dx, right? And I've got x minus 1 dx, not 2x minus 2. But could you factor a 2 out of this and divide it? What if you factored a 2 out of this? It'd be 2 times x minus 1. It would be this thing. That's what I'm saying I noticed about it when I decided up there that it would be u substitution. So say we divide both sides by 2. We get du over 2 is equal to x minus 1 dx. And that's what makes it work, right? Like so. Okay, so right here, these two things substitute successfully. I'll get 1 over u. That x minus 1 dx is du over 2. So let's like put a half right there and put the du. You know, the du over 2, I would just factor out a half anyway. So it turns out we get 1/2. What form is this? What's the antiderivative of 1 over u du? It's natural log absolute value of u plus c. In other words, 1/2 natural log absolute value x squared minus 2x minus 1 plus c. Okay, so that's how this second part right there in this integral is done. So, okay, now I'm going to go back to my original problem. Given that I showed you this, there's my result for the second part, okay? So, okay, that turns out to be this. Antiderivative of 1 with respect to x is x, and then minus, and I found that one to be 1/2 natural log x squared minus 2x minus 1 plus c. Okay, and then we got it at that point. But the division is what made it possible. I can't, at least me, I'm not saying there isn't a way to do it the way it is, but I can't think of a way to do it the way it is. If I divide it and I write this way, well, then it's pretty easy. I think it could be agreeable that we can figure out how to do that one because it's just use substitution. Okay? All right. So that one's down. Let's look at, we should do another one with division, I think. So let's look at this one. Okay, so why does this one involve division like the last one? Well, so I said that the rule was that this power here, this degree, this highest power, needs to be more than that one. And if it isn't, that's when you'll divide and go from there. All right? So that's a 2, that's a 3. This needs to be bigger than that. It isn't, so we divide. This is like an improper fraction. We'll divide it and we'll get something more like a mixed number. All right? Okay, so I think I have established that we do need to divide it. All right, so we'll do that. And that will look this way, x squared minus x, and I'm dividing into x to the third power minus x. Well, let's do this. Let's do this. You know how I said there's place values? Like there's x to the third power, but there isn't an x squared, is there? Maybe it would be more helpful to do that. You don't have to do it like that if you don't want to, but it might help you keep track of things. So I got 1x to the third power, no x squares, negative 1x, and then plus 1. If you like to put the 0 in, we'll do it. In fact, that's why, you know, when we write numbers like 101, that's a 1, no 10s, and 100. We can't just leave the 0 out because then it will look like 11. All right, so here, you know, it's maybe the 0 helps you follow it a little bit better. All right, so I got what I'm dividing into right there, dividing by x squared minus x. Okay, so let's see. I want to choose something such that when I multiply by this, I'm going to get x to the third power. That would be x. So if I do that, I'll get x to the third power. X times x squared is x to the third power. X times negative x is negative x squared. Okay, so I chose this. I multiply it by that. Here's what I'm looking at. Then I subtract. So that will amount to subtraction here, but it will amount to addition right there. Okay, so 0x squared plus x squared, that's going to be x squared. And then minus x, you know, what do you add to it right there? There's no x's, and then 1, and there's no constant. So minus x plus 1. Okay, if you wanted to, you can write plus 0x plus 0 if it really helped you. All right, so that's where we get this. Now we continue, and we'll say plus 1. Why do I choose a 1 now? What's 1 times x squared minus x? It's x squared. It'll match that. That's the objective, is to choose, multiply, and match the leading term here. So I'll get x squared minus x if I do that. And I guess plus 0 if you want. Okay. All right. So then I subtract, which amounts to subtraction and addition. And x squared minus x squared, nothing. Negative x plus x, also nothing. 1 and 0, 1. Okay, so I have my mixed number. This will divide out into x plus 1 over x squared minus x. Okay, all right, so let's continue from there. I'm going to rewrite my problem. Okay, now I've divided, so let's see, x plus 1 plus 1 over x squared minus x. Okay, so now I'm looking at this. The x is not a problem, neither is the 1. But what about that? 1 over x squared minus x. What am I going to do with that? Well, so that one, I mean, it's not use substitution. It's not like anything we saw until we got to this point, all right? Or at least to be humble, like I can't think of any way to do that besides partial fractions. Okay, so let's do this. We're going to pick up from this part here in a minute. This is the part that I'm a little bit concerned about. Okay, I think we can get it to work by partial fractions, though. So here's what I mean by that. That would be 1 over x times x minus 1. Am I correct about that? So it's conceivable to think that this is some number a over x plus some other number b over x minus 1, given that those are distinct linear factors. So I took 1 over x squared minus x. I considered that it's probably partial fractions. I need to see that factored, so I factored it. And then I think that that's the breakdown. Let's see. How is it going to work out from there? Don't we do like that? The very first problem I did for you, I showed you a lot more detail about getting a common denominator and adding the fractions and so on. But this is where you end up. And then, don't we end up here and here? If we multiply and regroup terms. And then could we say that a plus b needs to be 0 and negative a needs to be 1? Wouldn't that be the case? All right. Now again, the first few times we did these, I showed you a lot more detail. And you can look back at those other examples for something very similar to this one. Okay. So I get that a is negative 1. And if a is negative 1, that makes b equal to 1, according to those. All right, so I got it. So here's what our integral becomes, okay? So I'm going to leave the x plus 1, this I broke down this way with that a and b. All right, so here goes. Our integral becomes x plus 1 plus, let's see, a. Negative 1 over x. Okay? Plus b, 1 over x minus 1. All right. And this is all stuff that we can handle. All right. Those are, well, this one is u substitution. It's going to be 1 over u du. This is just straight natural log. That's an x, that's a 1. Okay, so here's what we're going to get. X squared over 2. That's the antiderivative of x. Plus x. That's what we get from the 1. Minus natural log, absolute value of x. Plus, this one here will just be 1 over u du. All right, so that will just be natural log, absolute value x minus 1 plus c. All right, there we go. So, all right, that's a big problem. It required a little bit of everything. But, you know, that's one reason why I wanted to do it. You've got the division aspect to it. Once you do that, you've got something that needs further breakdown by partial fractions. Okay? So I thought, well, you know, for the video, it'd be a good comprehensive problem to show you. Anyways, let's look at one more problem. All right? So this is the one I had in mind. All right? Now, the reason why I wanted to do this one is because, you know, sometimes we can see an unfamiliar problem, but with a little substitution, it can become one that we're a little more used to. Okay? All right. So this one at face value with secant squared and tangent squared doesn't really resemble these that we've been working on. Okay? It seems because it has more than just x. It has functions of x like secant and tangent. It seems beyond the others. But it might be that with a substitution, we can turn this one into one like what I've showed you. All right? So let's just try a substitution. And what I mean by that is here I'm working with the variable x. And a substitution could change this over to the variable u. What I mean by that is here I have the variable x and the differential dx. Perhaps I could get a substitution that would turn it into u and du. And then maybe that would look a little more familiar. Now the reason why it strikes me that I could do this one that way is because I see tangent and I notice, well, the derivative of tangent is secant squared. It's like the u and the du are all right there, okay? So let's try this. Let's say u is tangent. And as a result, that would be u squared, right? And then du is, well, derivative of tangent secant squared. That's what I was noticing from the beginning. Du is secant squared x dx. So yeah, we could easily make that substitution. I guess the bigger question is, sure, you can make this substitution, but do you end up with something that you know how to work? What good is a substitution if you get something that you can't figure out as well, right? So let's see. Between secant squared x dx, that's going to be du. I'll get 1 over u squared minus 1. So let's see. 1 over u squared minus 1 du. Okay? Now then, so say we make that substitution. We get this. All that's correct. What if we get stuck here? Well, then maybe the substitution wasn't the way to go. All right? But I think that we can handle this one. See, that's a difference of 2 squares, right? So yeah, I could definitely handle that. I could try partial fractions. I could look at it like this. 1 over u squared minus 1 is equal to 1 over u plus 1 times u minus 1, which is a fraction containing distinct linear factors. So it's conceivable that it can be broken down this way, right? That's the whole notion of partial fraction decomposition, that these have this common denominator. So it's conceivable that you could add these together with the correct numbers a and b and get that. And if we could break this down into this, that would be easy to do up there. It would be easy to work this one out. That one, not so much. This one, yes. Okay? All right, so how do we proceed from here? Well, we need to add these together and make it be equal to that. The way that that's going to look is a times u minus 1 plus b times u plus 1. That's what it would look like if I got a common denominator of u plus 1 times u minus 1. That's what the numerator would be once these are added together. But I need that to be what? I need it to be this number. I need it to be a 1. So I get like so. Okay? All right, so from there, I'll multiply, I'll combine all like terms. What I'm going to get is a plus b times u minus a plus b. Okay? Or I'm doing that exactly like I would have done problems before. I'm skipping a few more steps now, but I'm doing it the same way. So, okay, now what's this say about a and b? Well, is there a u over here? No, I don't see one. So a plus b needs to be 0. This has to be 0u. And then what's negative a plus b need to be? That needs to be 1. This number needs to be 0, and that number needs to be 1. 0 times u plus 1, right? That's why I say a plus b, 0, negative a plus b, 1. All right, so we can, let me see, I think I've solved all the other problems by substitution, so I'll do this one that way. It's obviously not the only way to solve a system of linear equations, but it's what I've done. So we could initially solve that first equation for a and say a is negative b. And then we could take that, we could substitute it in the second one. What if we took a and substituted negative b in its place in that second equation? It would say negative b plus b is equal to 1. It would say 2 times b is equal to 1. Or it would say b is equal to a half. All right? Okay, so b is a half. If a and b add to 0, that means a's got to be negative half. All right, so I've got it. I've got the breakdown. A is negative half, b is half. All right? So let's take this, go a little bit further. Okay, so I had this. I figured out the decomposition. So it's going to be negative 1/2 over u plus 1 plus 1/2 over u minus 1. These are, I hate to say u substitution again, but it's true. Just think about it like if this was negative 1/2 x plus 1 plus 1/2 x minus 1 dx, then I would say, well, that's a u substitution, 1 over u du. It's a little bit awkward to say that now, given that I've already done one u substitution, but you could do another, and that's all this is. So here's what you're going to get. Negative 1/2 natural log u plus 1. But u is tangent. So tangent x plus 1 plus 1/2 natural log u minus 1, but u is tangent. So tangent x minus 1 plus c, and then we've got it. Okay, so technically 2 u substitutions are required. You know, there's other letters of the alphabet. You could make a substitution again, but it wouldn't be u. But let me just point out that, yes, this would be another substitution, but it's still that natural logarithm form. Okay? All right, so that's that one, 2 substitutions. But, you know, we take something that we don't so much recognize, and through one substitution, let me just focus on and try to emphasize that we get something that fits into that same method that we've been learning in these past few videos.